evaluate both sides of the if and then do a 1-0 linear interpolation of the if. Okay. So, all right, so we have three major kinds of per frame functions, and this is kind of where the value add to PixelBender comes into the equation. Evaluate dependence is sort of our general purpose sort of stage where you can just do any kind of computation. You take parameters in, you produce dependence on the other end. We have this thing called region reasoning. So image processing is somewhat complicated. It seems simple. You know, you take an image and you take a pixel and you do some stuff to it and you squirt a new pixel down. But if you're trying to, say, twirl an image or blur an image, the amount of the image that you need at the end of the day might be different than the amount of the image that you start with, vice versa, depending on if you're going which way, or if you're like expanding, dilating. And so this needed and change are two functions that we allow the third-party author to write that answer the question of, if I want to produce this region, how much of this input image do I need? And if you're chaining a whole bunch of filters together in series, you need to be able to sort of pass that question this way, pass that question back, and then evaluate everything in turn. So that's a region reason. I'm not going to talk a whole lot about it. We have tons of stuff for this in our documentation online. And generated is for pixels that don't have input. It's like, how much of the plane does this kernel generate? It's good for things like Mandelbrot sets and stuff that run blazingly fast on GPUs. All right, so this is kind of our order of operations. We pass in kind of, we want to produce a certain amount of a region. Some portion of an image has been exposed on a windowing system. The windowing system tells us, hey, we need to evaluate this much of the image. We run evaluate dependence, and this always happens via code jitted up with LLVM. And then we run our region reasoning to determine how much of the input images we need to get in order to produce a desired output image. And this is also always run on LLVM generated code. And then the last stage is we evaluate the pixels. Now, we prefer to run on the GPU, clearly. GPUs just win for this kind of operation all the time, ever, always. But there's a lot of circumstances, and I'll talk about them a little later, when we can't run on the GPU. And so in that case, we will jit up the code with LLVM and run via that path. And so the one little side thing is if you're chaining a whole bunch of these things together in series, the evaluate dependence and region reasoning for all the stages occurs prior to the evaluate pixels of any stage starting. So. Okay, so why do we use LLVM to evaluate pixel when GPUs kind of always beat us? First, we have to handle a really wide array of graphics cards. You know, game programmers get to basically say, hey, if you don't have a DX11 or DX10 graphics card, this game won't run, or you need at least a DX9 or DX8. We don't have quite that level of ability to dictate to our customers. And so when we're sort of come face to face with an old graphics card, we want to still be able to run, and so we run on the host machine. In particular, things like loops, branches, breaks, continues, ints, and bools are kind of newer features on graphics cards. And also, even if you have something that can work on a graphics card, like say you're taking an image and you're twirling it, as you twirl it, or if you do a really like wide kernel box blur, you might get this thing where the evaluate of an individual pixel takes so long that the overall kind of timeout period on the graphics card gets hit, in which case you can't run it. Even though it's expressible on the graphics card, it's not really runnable. So we have a lot of problems with graphics card drivers, both on Mac and PC, and from all graphics card vendors. We always deal with it. We aren't games, and so we use a wider array of the graphics card driver stack than a lot of games do. And so we often find some problems. So we'll use the CPU, and then sometimes also I'll talk a little bit more about this later. GPUs, at least via the GLSL path, don't have great numerics. And so sometimes we want to use the CPU in order for getting final render. And also, a related problem is when you need consistency. If you're, say, twirling an image in a video stream, and as you animate that twirl parameter up, at some point during that stream, it gets thrown off the card because the extraction count limit gets hit. Now, if you're trying to use the GPU to do final render for a video stream, all of a sudden your numerics pops off the graphics card and onto the CPU, and you get slightly different results. And that's really unacceptable. And so you might have to use the CPU just to maintain consistency of the floating point math. Okay. So I'm going to talk a little bit about the overall structure of the language. And this is basically the task that we had before us for getting down to the LLVM IR. So we have, like all shader languages, we have scalars, and we have vectors, and we have matrices. And these are all pretty much first-class data types. And you can add vectors, you can do really weird, strange things like subtract ints off vectors, and it promotes them up to vectors, and it's quite sort of, actually it's a little bit weird. And from someone who comes at graphics from more of a mathematical background rather than a hacking background, some of the things that you can express are revolting. But the world really likes to be able to subtract a scalar off of a vector and have it produce a vector. So I will oblige the world. And so our operators, we have scalar operators, vector operators. Matrices, we have a lot of component-wise operations. Most of the multiply operators are all sort of linear algebra operations. We also have component-wise matrix multiply as a primitive in the language. So, all right, so the other thing about scalar languages is, shader languages is they have a wide array of intrinsics in the language. And we're no exception. We have all of the sort of standard kind of, sort of trigonometric operations and some sort of various graphics operations like clamp and mix and smooth step. In general, these are all vector-capable operations. So, like the sign of a float 3, it produces the component-wise sign of the input vector. Okay, so a whole bunch more. Sorry about the slide reformatting. Apparently, moving it off of my PC onto my Macintosh was bad. And of course, the sample bilinear and nearest point sample as well. And then some Boolean vector operations. Okay. So just to recap, we have matrix. We basically have a matrix, vector, and intrinsic heavy language, and that's the language that we had to cast down into LLVM IR. We have no recursion, and